Welcome, dear students, to the course Physical Optics and Modern Optics. We are going through the chapter Matrix Methods, and today let us work out a few problems from the reference textbook of Optics by Brijlal Subramaniam and Avadhanalu. The given example is the focal lengths of two thin convex lenses are 20 centimeters and 10 centimeters. They are at a distance of 10 centimeters on the axis of symmetry. If a point object of length 1 centimeter is placed at a distance of 20 centimeters from the first lens, find the position of the image and magnification. Okay, now let us write down what are the given parameters. For that, assume the axis of symmetry or the z-axis. Okay, now two thin convex lenses of focal lengths 20 centimeters and 10 centimeters are there. Now they are 10 centimeters apart on the z-axis, right? Now a point object of length 1 centimeter is placed at a distance of 20 centimeters from the first lens. So U is equal to 20 centimeters. Now we have to find what is the position of the image and its magnification. Right. Let us understand the different operations undergoing here. Now the rays from the point object first translates through the medium towards the first lens. So the first operation is translation. Let us call it T1. It can be represented by the matrix 1, 0, d by mu 1. Here the values will give 1, 0. D is 20 centimeters. That in meter becomes 0.2 and again 1. Now the second operation is that of the lens. So light undergoes the system matrix S1 of the lens L1. I can write the matrix form 1 minus of P1 plus P2 0, 1. I use the system matrix for the thin lens because the thickness has not been stated. Here minus P1 plus P2 gives minus P dash 0, 1, where P dash is the effective power of the first lens. Okay. In terms of focal length, I can write it as 1 minus 1 by f dash 0, 1. And substituting the values, I will be able to write 1 minus 1 by 0.2 in meters, 0 and 1. This is the system matrix for the first lens. Now, after traveling through the first lens, again light travels 10 centimeters towards the second lens. So it undergoes translation again. And this can be represented as 1, 0, d by mu becomes 0.1, 1. This is in meters. Now, when light reaches the second lens, again it undergoes a system matrix for the second lens, and it can be written in terms of focal length as 1 minus 1 by 0.1, 0 and 1. And finally, after the second lens, light travels towards the image plane and forms the image at that plane. So light translates to that point, again undergoing translation matrix. And that can be represented as 1, 0, d by mu. D is the distance towards the image. Mu is 1 because light travels through air, and this is 1. Okay. So these are all the operations taking place when light travels from the object towards the image plane. Hence, to find out the image plane, or the system matrix for the image plane, we take the product of all these operations in the reverse order. Okay, so I can write system matrix of the image plane as matrix T3 product over matrix S2 product over matrix T2 product over matrix S1 product over matrix T1. Right. So let's substitute the values for each matrix. We get 1 0 V1 into 1 minus 1 by 0.101, and T2 is 1 0 0.11. S1 is 1 minus 1 by 0.201, and T1 is 1 0 0.21. Taking products. First, let us find the product of these two matrices, and then let us take the product of these two matrices the next step itself. Okay. For the first product will be 1, then minus 1 by 0.1, then V, then 1 minus V by 0.1. Okay. Now the next product will be product of these two terms. That is 1 minus 1 by 0.2, right? And this term is 0.1, and the next term is 0.1 minus 0.1 by 0.2 plus 1, right? The remaining term is 1, 0, 0.2, 1. Now taking the product of these two terms, this term is actually 0.1 by 0.2 gives 0.5. So 1 minus 0.5 is 0.5. Okay. Taking product of these two terms, we get matrix 1 minus 1. Then we get minus 1 by 0.2, 0.5 by 0.1, that is 5, so minus 5. Then V plus 0.1 minus V, and the next term minus V by 0.2 plus 0.5 minus V into 0.5 by 0.1 into matrix 1 0 0.2 1. Okay. So the system matrix of this image plane can be written as matrix S is equal to, first term is 0, second term becomes minus 10, this term becomes 0.1, and this term becomes 0.5 minus 10V. Okay. Into matrix 1 0 0.21. Okay. Again, taking products, I can write 0, minus 2, minus 10, then 0.1 minus 2v plus 0.1, and the next term 0.5 minus 10v, right? Okay. From the condition of the image plane, we have this term to be equal to 0. Okay. So from the condition of image plane, zero point 2 minus 2v is equal to 0. That implies 2v is equal to 0.2 and v is equal to 0.2 divided by 2 is equal to 0.1. That is 10 centimeters. Okay. To find magnification, this term is equal to m. Okay. From the system matrix of the image plane, it was this term that corresponds to m. So I can write magnification m is equal to 0.5 minus 10 times v gives, I take the meter form, 10 times 0.1 is 1. So this will be equal to minus of 0.5, that is minus 1 by 2. So from this I can infer that the image is inverted and it is half the size of the object. Thus, the image will be obtained like this. Now in the next example, we have a thick biconvex lens having a radius of curvature plus 6 centimeters and minus 6 centimeters, which is made up of a material of refractive index 1.6. If the thickness of the lens is 2 centimeters, find the system matrix and focal length. So here, a lens of defined thickness is given, right? So we use the system matrix for a thick lens. Before that, let us write down what the given parameters are. So the radius of curvatures are given. R1 is equal to 6 centimeters, that is 0.06 meters, and R2 is equal to, the sign convention has been used, it is minus 6 centimeters, that is minus of 0.06 meters. The refractive index of the lens mu is given as 1.6, so it must be a lens made of flint glass. And the thickness of the lens is mentioned as 2 centimeters, that is 0.02 meters. Okay. Now, by formula, the system matrix of a thick lens is given as, in Gauss constants, matrix B minus A minus D C, where A is given as P1 plus P2 minus P1 P2 T by mu. B is given as 1 minus P2 T by mu. C is given as 1 minus P1 T by mu, and D is given as minus T by mu. Let us calculate the values for all these Gauss constants. For that, we need to find the values of P1 and P2. P1 is equal to mu2 minus mu1 by r1. That is, mu2 is 1.6 minus mu1 is refractive index of air, 1 divided by 0.06. That gives 0.6 divided by 0.06, that is 10 meter inverse or 10 diopter, the unit of power of a lens. Likewise, P2 is equal to mu1 minus mu2 by R2, that is 1 minus 1.6 divided by minus of 0.06. That again gives 10 meter inverse or 10 diopter. Thus, Gauss constants can be obtained as A is equal to P1 plus P2, 10 plus 10 minus P1 P2 into T divided by mu. You can do the math. 20 minus 1.25, that will be equal to 18.75. You can pause the video and do the calculations. Okay, B is equal to 1 minus P2 T divided by mu. That is 1 minus 0.125, that is equal to 0.875. You can pause the video and do the calculations. Then 1 minus P1 T divided by 1.6, that is mu, again gives 0.875. Okay, and D is equal to minus T by mu, that is equal to minus of 0.0125. The system matrix of the thick lens is obtained as, in place of Gauss constants, I am going to write the values 0.875 minus 18.75, 0.0125 and 0.875. Okay, so this is system matrix of this thick lens. To find the focal length, we get it from this term A. So we have this relation focal length F is equal to 1 divided by A. Okay, so 1 divided by 18.75 is equal to 0.0533 meters. That is equal to 5.33 centimeters. Now the next example is to calculate the focal length of a Ramsden's eyepiece. Now what is a Ramsden's eyepiece? It consists of two plano-convex lenses, each of focal length f, and they are separated by a distance of 2f by 3. So we have two plano-convex lenses having focal lengths f, and they are separated by a distance of 2f by 3. So first let us derive the system matrix of this Ramsden's eyepiece, and for that we have the light undergoing different operations here. First, light will be transformed by the L1 lens, then it will translate through a distance of 2f by 3, and again light gets transformed by L2 lens. So the three operations light undergoes here is, the first one, it undergoes the system matrix of the first lens SL1 given by 1 minus P, power of that lens, 0, 1. Okay. The P is actually P1 plus P2, that is the sum of the powers of the refracting surfaces of that lens. Okay, P1 will be the power of the first surface, P2 will be the power of the second surface, and the combined power is given here, capital P. In terms of focal length, I can write it as matrix 1 minus 1 by f, since focal length f is defined here, 0 and 1. Okay. Light then translates through a distance 2f by 3. So the translation matrix can be written as 1, 0, d by mu, that is 2f by 3, mu is equal to 1, index of air, and 1. Then again light is transformed by the second lens, and the system matrix for the second lens SL2 can be written as matrix 1 minus 1 by f. Focal length is the same. So minus 1 by f, then 0, 1. Okay. So the resultant system matrix of the Ramsden's eyepiece can be written as product of SL2 over T over SL1 in the reverse order. Okay. You can do the math and find out the system matrix of this Ramsden's eyepiece. And you will be getting a matrix of the form having Gauss constants B minus A minus D C. The term A gives the focal length of this Ramsden's eyepiece, and it is given as A is equal to 1 by F, where F gives the focal length of the Ramsden's eyepiece. The next problem is similar to the earlier one. Here you have to find the focal length of the Huygens eyepiece. Now, a Huygens eyepiece is of two plano-convex lenses again, but they have a focal length of 3f and f. So the two lenses have different focal lengths. One is having a focal length of 3f and the other is having a focal length of f. And they are separated by a distance of 2f. So you have two plano-convex lenses, focal lengths 3f and f, and they are separated by a distance of 2f. Now to do this problem, you need to find out the system matrix of the Huygens eyepiece. You can do the mathematics and calculate the focal length of this Huygens eyepiece. The problems 4 and 5 can be submitted as the assignments for today. Thank you.